Okay, so the next step in what we're doing here now is to start looking at what happens when we put compounds together. All right, when we mix two compounds, there is a possibility that their chemical properties now, and not their physical properties, may cause them to have a chemical reaction with each other. All right. Now, the things about a chemical reaction. Okay. First off, a chemical reaction happens if a more stable state can be reached by the two compounds because of the reaction. Okay. Usually a lower energy state. So most of the time, energy is released, except in a few rare endothermic reactions. In a chemical reaction, when it's all done, what do I have at the end compared to what I had at the beginning? Okay, I have the same elements. Do I have the same materials? No, I don't. Okay, the chemicals, remember, according to Dalton's atomic theory, it said that in a reaction, atoms can be separated, joined, or rearranged. So while I'll have the same atoms, and not just the same ones, but the same number as well, okay, the law of conservation of matter comes into play here as well. I can't create or destroy matter in a chemical reaction. So not only do I have the same atoms I started with, I have the same number of all of those atoms as I started with. And that's why it's important to be able to balance a chemical reaction. And it's the balancing part where being able to write chemical formulas is really important. Because if you don't write the formulas right, you'll never make the reaction balance. Okay? So, tip. If your reaction doesn't balance, you probably didn't write a formula right, and you should go back and check them. All right, but we'll get to that later. Okay, so the big thing we need to understand here, guys, is that in a chemical reaction, our materials are chemically different at the end. Okay, they are chemically different at the end. That is, they have been either separated, joined, or rearranged. What are some signs that a chemical reaction has occurred? Okay, there could be a new odor develop. There could be a temperature change up or down. There could be a state change. So that could be something like a precipitate being formed. We talked about that yesterday in the solubility lesson. Color change. We already talked about the temperature change, yeah. Right, if there's bubbling or fizzing. And oftentimes with bubbling or fizzing, we detect a change in odor as well, because bubbling and fizzing is evidence that what has been produced? A gas, yeah. Okay, does that mean that every time a gas is produced, there'll be bubbling and fizzing? No, it doesn't. Okay, in fact, one of the reactions that you're going to do in your reaction lab is going to produce ammonia, which is a gas, but it will not bubble and fizz in any way. Okay, but it'll start to stink almost right away, okay, as soon as you mix the two. And it's a powerful stink because I mix everything uber concentrated. Okay, when a reaction happens, I like to be sure about it. Okay, I want to make sure I see it all. Right. Okay, so the signs of a chemical change, we seem to remember those. That's good. We're going to look at the 5 basic types of chemical reactions. There are more than that, but we're going to look at the 5 basic types. Okay, understand how to identify each reaction type. Each one has something unique about it. Okay, so they're actually fairly easy to identify. And then learn to write them properly, balance them. Okay, all of that kind of important stuff. Okay, so what the expectations are for you to be able to do, not necessarily at the end of today, but after a few days of practice, is to be able to identify a reaction just by looking at it, okay? To be able to write it properly, so have all the formulas correct, okay? And to make sure that you have the same number of every atom type on both sides, okay? We'll get to eventually only having the reactants and having to predict the products. Okay, that'll be the next thing, where I only give you the first half of the reaction and you have to tell me, here's what's going to happen. Okay, here's the things that will be formed. Okay, so in a chemical reaction, big thing, the final products are chemically different from the starting reactants. Okay, so here's 2 terms we need to know: products and reactants. Right? A reaction starts with reactants. They're going to react. Products are what is produced as a result of the reaction, which sometimes we actually try and make things make sense. Okay, here's one of those times. Right? But the big thing to remember is they are going to be chemically different than what we started with. That doesn't mean we're changing the atoms. We have the same atoms we started with, but they're in some new order, combination, whatever. Okay, so a sample reaction could look, let's say, something like this. Um, okay, these would be my reactants. Okay, because they're the things that are going to react. Okay, these would be my products, what would happen after the reaction. Okay, so this side of the arrow, okay, and this is an arrow. We don't use an equal sign in a chemical reaction. It's always an arrow, okay, because an equal sign would be, yeah, that would be saying that this equals that, and definitely doesn't. Okay, we said it's chemically different on the other side, so we can't use an equal sign. Okay, it's this leads to this. I just say that because I often see people use equal signs, and I don't know why. Okay, it's not math. So these are our products. Okay, this is a relatively straightforward, what we call double replacement reaction. We'll get to the types here in a minute, but this is a double replacement reaction in which two ionic compounds react and form two new ionic compounds. All right. Now, you can see that the metals essentially switched partners. Okay, I didn't end up with two metals together here and two non-metals together. All right, why wouldn't that happen? Right, metals don't chemically bond to each other, right? So I could never have a reaction where that would happen. Okay, so that would be an example there. Again, reactants are what we start with, products are what we end with. Okay, now one last thing that I have to do with a chemical reaction is I have to make sure, Mason, I have to make sure that I have the same number of each type of atom on both sides of the reaction. This is what we call balancing the reaction. It makes sure that I haven't created any matter magically or magically destroyed any matter, right? So how many magnesium atoms are on this side? Okay, how many over here? One. Okay, so is it balanced? Okay, it's good. All right, how many iodine atoms? Two. Okay, over here? Two. All right. How many nitrate ions on this side? Two. Two. Okay, so are we good? Everything's balanced? Sorry, and the lead is also balanced. That one's easy just because everything is already balanced. It's not always that easy. Okay, if it isn't perfectly balanced, can I change these little numbers? No, I can't, because I already swapped and dropped these compounds to get those numbers. What I can do, though, is change how much of this whole material I have by adding what's called a coefficient, putting a big number here, like a 2 or a 3 or whatever it is that I actually need. In this case, I don't need that number there because everything was a 1, right? Everything was already balanced. So that's kind of where we're headed, is being able to write the reaction out and then make sure that there's the same number of everything on both sides. All right. The 5 reaction types. We'll start out with the simplest. The simplest type is a synthesis reaction. Okay? In a synthesis reaction, I make a single compound from 2 elements, usually 2 elements. Sometimes it's an element and a compound, but most of the time it's 2 elements. Okay, so in the synthesis reaction, 2 or more elements react to form an ionic or molecular compound. Could be either one. Okay, so what we see here is we have 2 magnesium atoms reacting with 1 oxygen molecule, okay, to form 2 molecules of magnesium oxide. Okay, is that equation balanced? Yeah, it is, right? There's 2 magnesium atoms, and on this side, there are 2 magnesium atoms. On this side, there are 2 oxygen atoms, and how many are there here? 2. This 2 applies to the whole thing. Okay, it's like it's in brackets, but it's saying that there are 2 magnesium oxide molecules, right? That means there's 2 magnesium atoms and 2 oxygen atoms. Right. Okay, and then the reaction down below, similar. Okay, I've got potassium reacting with bromine. Again, 2 atoms of potassium reacting with 1 molecule of bromine that contains 2 atoms. Okay, and that's going to make 2 molecules of potassium bromide. Let's track it. Okay, good question. Why isn't it written like this? Because this little 2 implies that the 2 are bonded together. That's why this one has a 2. Bromine's one of those molecular elements where the 2 atoms actually chemically bond to each other. Okay, potassium doesn't do that, so I'm saying there are 2 atoms of this. This is one molecule containing 2 atoms. Okay, does that make sense? That's a good question. All right, so synthesis reactions make sense? Right, they're pretty straightforward, right? And if you were predicting the products of one of these, they're also pretty straightforward. Oh, okay, well, I put them together then, right? I just put them together, drop and swap if it's going to be ionic, and you're off. Okay. All right, the exact opposite of a synthesis reaction is a decomposition reaction. So in this case, we start with a single compound and we break it down into its constituent elements, or in some cases, constituent ions. Losing my patience over here. Okay, so prime example would be liquid water. If I run a very strong electric current through liquid water, I can actually get it to separate. Okay, it's actually the process by which rocket fuel is made. Right, they get liquid hydrogen, liquid oxygen for making rocket fuel. Right, but when they separate the 2, they're a gas. Then they put them under pressure, turn them into liquids, and then you can use them for rocket fuel. Okay, so in this one here, I have 2 molecules of water breaking down into 2 molecules of hydrogen and 1 molecule of oxygen. Right? So I've broken it down from one compound into 2 elements. Okay? How would I know to make these both 2s? Yeah, because oxygen's a diatomic element and so is hydrogen. Did we highlight those on our periodic table? Okay, that's why we did it that day, in preparation for this day. Right? We have to know which ones end up as 2s, because they don't all end up as 2s. Okay? And as Strachan asked earlier, why didn't you just write a 2 beside potassium? Well, I didn't, because potassium doesn't do this. Okay? Only some elements do. So I have to look for those, okay, those kind of special elements to see if they're present when I make my products. All right, is this reaction balanced? How many hydrogens do I have on this side? 4. Okay, I have 2 water molecules. That's what the big 2 means. And I have in each water molecule 2 hydrogens. So you just multiply everything behind this number to get your number. So 2 times 2 is 4. Over here, I also have 4. Right? On this side, I have each molecule containing 1 oxygen, but there's 2 of them, 2 molecules. So 2 times 1 is 2. And over here, I also have 2. Question? Oh, sorry. The L's and the G's. Liquid, gas. Liquid, gas, solid. AQ stands for aqueous. Okay. When I write the reactions, I sometimes do that and I sometimes don't. You guys never have to worry about that. Okay, in Science 10, but you will when you get to Chem 20. Just habit that I sometimes do it. Okay, I'm breaking that habit because I don't teach Chem 20, so don't always do it. All right, and another example here of a decomposition reaction. So I've got nitrogen triiodide, and it's breaking down into nitrogen gas, which is a diatomic, okay, and iodine, which is also a diatomic, right? So I get these 2 molecules breaking down into 1 molecule of nitrogen and 3 molecules of iodine, okay? But again, you can see that this equation is balanced. I have 2 nitrogen atoms on this side, and I have 2 nitrogen atoms on that side. And I have 6 iodines, 1, 2, 3, 4, 5, 6, okay? And I've got 6 of them over here as well. Okay. Questions so far? Okay. Oh, this is where I was going to highlight those special elements. Everyone's got those highlighted on the periodic table, right? Okay, I'm going to skip that part. Okay, combustion reactions. Combustion reactions are different from every other type by 1.5 miles. Okay, they involve a reaction always with oxygen. Okay, you can't have a fire without oxygen. Okay, so they always involve oxygen, and they always involve what we call a hydrocarbon. Right? And a hydrocarbon is a molecular compound that contains carbon and hydrogen. Okay? These are essentially our fuels. Right? So in this reaction, we have C3H8 reacting with oxygen gas. And here's the thing about combustion reactions. The products are always the same. the products of a combustion reaction are always carbon dioxide and water. The only thing that will change is how much carbon dioxide and water get produced. Okay? The bigger the fuel, the more carbon dioxide and water will be produced. Okay? What's the common name for C3H8? We use it a lot, actually. It's used in your barbecue. Hmm? Oh, okay. Wow, you got I got charcoal as an answer there. That's cool that people still use charcoal barbecues. Propane, yeah, propane. Okay, this is propane. Charcoal barbecues do it. It's actually better flavor in charcoal barbecue. But yeah, anyway, it's also way more trouble. It's way easier to just light a propane barbecue and throw the steaks on. But all right, so this is propane. Okay, propane gas reacting with oxygen gas or burning in the presence of oxygen gas, producing carbon dioxide and water. All right. Now, there's a couple of kind of special rules to do with combustion reactions. The first rule is that the products are always carbon dioxide and water. Okay. Okay, so that's the first kind of special rule about combustion reactions. If you see a hydrocarbon reacting with oxygen, the products are automatic, CO2 plus H2O. Okay. You read my mind, I'm just about to get to that. Yeah. Okay, so the question was, how do you calculate how much carbon dioxide and how much water is going to be produced? The answer is, when I balance the reaction, I'll figure it out. Okay, so in this one here, I'm just going to rewrite it kind of from the beginning so you see the process. Okay, so we've got C3H8 plus oxygen gives us CO2 and water. All right, how many carbon do I have on this side? 3. Okay, how many do I need over here? Okay, so I'll just do this. No, okay, I can't do that because that makes that no longer carbon dioxide. Okay, so I can put a big 3 right here. Now there are 3 carbon dioxide molecules. Right? What should I balance next? Actually, I should balance the height. This is the other trick. I'm sorry, I set you up. Okay, the other trick is that we always have to balance a combustion reaction alphabetically. It just works out that way because oxygen messes stuff up. No matter what reaction it's in, oxygen messes stuff up if you try and balance it first. Okay, so the second rule, maybe we'll just go right back up here and write the second rule. Balance alphabetically. Okay, so that would be CHO. All right, so the next thing I'm going to balance is the hydrogens. How many hydrogen on this side? 8. Okay. What do I need to put in front of water to get 8 hydrogens? 4, right, because 4 times 2 is 8. Okay, so this is why I'm balancing oxygen last. I now know how many oxygens are on the product side because there's numbers in front of both compounds now. Okay, everybody follow me there? Okay, oxygen's in 2 places. It makes it harder to balance. All right, so 3 times 2 is how many? 6, plus how many more? 4. Okay, 6 plus 4 is 10. Okay, so over here, what do I need to put in front of O2 to make 10? 5. Okay, and we're done. We've balanced it. Okay, that's how balancing works. Generally, with the exception of combustion reactions, you start with whatever's in the largest number. Start with whatever atom is in the biggest number. Balance it first. It generally works better to do it that way. Okay, but with combustion reactions, we always balance alphabetically. No, I didn't know how much I needed at the start. Right? All I knew is I had this. Okay? If I have one of these, how much is it gonna make over here? And I can work backwards. Okay? In a combustion reaction, it just works that way. In other reactions, you might balance in a different order because, like I said, you generally start with the largest number first. Okay, there's one more rule. And it's going to happen when you get a compound that looks like this. Okay. H18. This is the active ingredient in gasoline. What's the active ingredient in gasoline? No, not all gas contains ethanol. Some does. It's listed right on the pump, usually as a number. And it's different between regular, mid-grade, and premium. Octane. Okay, octane is the active ingredient in gasoline. It is C8H18. Right, it is a long hydrocarbon that releases a lot of energy when burned, makes it ideal for gasoline. Okay, also comes in a liquid form. Okay, so that's what we're dealing with right here. Now I want to start my balancing. What do I start with? Carbon. Okay, so how many carbons are here? 8. Okay, so we go over here and I put in 8 here. All right, how many hydrogens? So what needs to go over here? A 9. Okay. Now I got to look at my oxygens. I've got 16 oxygens here in the carbon dioxide, 8 times 2, right? And I've got 9 more here, which gives me 25. What times 2 gives me 25? And I can have half a molecule? No, I can't. Okay, so here's the third rule. Okay, the third rule is if the carbons are an even number, start with a 2. That'll eliminate that 0.5 we just ran into, right? Anything that's a half, if you multiply it by 2, becomes a whole number. All right, so third rule, okay? Even number of carbon, start reaction with a 2. RXN, by the way, is shorthand for reaction. I think shorthand is a dead skill now, though. Everyone has laptops. Just carbon. This is just for combustion reactions. Combustion reactions have their own set of rules for balancing. Everything else is actually more straightforward. That's correct. Yeah. Okay. So now if we go through this balancing, okay, we have 16 carbons. So I got to go over here and put a 16 here, right? And I have 36 hydrogens, right? So I'm going to take this 18 and put it here. 18 times 2 is 36. Everybody all right with that? All right, now looking at the oxygens, I've got 16 times 2, which is 32 oxygens, okay? And then I've got another 18 for a total of 50. Okay, I've got 50 oxygens on that side. What times 2 gives me 50? 25. Okay, now I got whole numbers, right? So you have to start with a 2 if it's an even number because it gives you whole numbers when you balance. You can't have a 0.5 as a coefficient when you're balancing, okay? Because then you're saying, oh, I just had half a molecule. You can't have half a molecule. That doesn't happen, okay? All right, so special rules for balancing the combustion reactions. Everything else, the rules for balancing every other kind of reaction is start with whatever's in the largest number and work from there. Okay, you'll get it to work. The first rule was that the products are always carbon dioxide and water. Okay, questions there? All right. Now, the next 2 types of reactions are very similar. Okay, they're both replacement reactions. The catch to replacement reactions is if there's compounds, they're ionic. There will be no molecular compounds in these reactions. There can be molecular elements, but there can't be molecular compounds. It's always ionic compounds in these. Okay? So the first kind of replacement reaction is a single replacement reaction. And in a single replacement reaction, we have an atom. It could be a metal and it could be a non-metal. It doesn't matter. Reacting with an ionic compound to form a new atom by itself and a new ionic compound. Okay, so it's atom and ionic compound, atom and ionic compound. Okay, it'll be the same on both sides. But what'll change will be what thing is in the compound and what thing is by itself. So for replacement reactions, you kind of have to think of it like people a little bit. Okay, and you have to remember here that chemistry is very old-fashioned. Okay, very old-fashioned. So let's say metals are guys and non-metals are girls, just for argument's sake. Okay, that's what we'll say, because that's the way my diagram goes. Okay, so this guy is by himself, and he sees this couple together, and he says, I like her, and he's a loser. So he comes in and rolls this guy, gets rid of him, takes off with his girl, and this guy walks off alone. Okay, yeah. Notice that again, chemistry is old-fashioned. The two guys didn't end up together here. Okay, because chemistry is old-fashioned. Okay, just chemistry. I'm not making any other things about that. Okay, you choose who you love. Who you love is who you love. Okay, but in chemistry is very old-fashioned. Doesn't approve of things like that. Okay, so yeah, we got in this case here. You have to have a metal and a non-metal end up together. Okay, that's what has to happen. Otherwise, it's not an ionic compound. Okay, we know that two metals can't end up together because they won't bond to each other. And if two non-metals end up together, we don't know how to put them together because we can't balance their charges. So okay, it just has to work out that way. I know the analogy is breaking down as times change, but it still sort of works.
Why does, like, you have that solid?
AQ, aqueous, means it's dissolved in water.
Yeah, so why? How come the
Silver, yeah.
How come the silver can be solid?
Good question. This is a very cool reaction, actually. Okay, if I set this up in the lab, if I take silver nitrate, this is a clear solution, and I put a penny in it or a piece of copper wire in it and leave it overnight, if I come back, silver will plate out onto the penny or the copper wire. It'll be covered in a thin layer of silver as the silver is replacing the copper. Okay, and the solution will slowly turn blue because the copper is reacting with the silver and replacing it. So that copper ends up in solution with the nitrate, and the silver ends up coming out of the solution and plating out as a solid. You're not going to get rich doing this. Okay, I know what you're thinking. Silver nitrate is really expensive stuff. We don't have very much of it because it contains silver, and you could do this. Okay, so yeah, it's actually very, very expensive to buy silver nitrate. And yeah, the amount of silver you would get to plate out would be worth next to nothing. It's not like you, oh, sweet, now I can make a ring. No. Okay. You'd be lucky if you could make an earring if you use like 3 gallons of the stuff. Okay, it's not, yeah, you're not going to get rich.
So, how do you know you're solid?
Well, silver, because silver is a metal, right? Silver is a metal. So when it comes out and it's by itself, it has to be a solid, right? That's just how silver exists. Yeah. Okay, so in a double replacement reaction, whatever is by itself replaces what it's like in the ionic compound. So since this is a metal, it replaces the metal. All right, if this was a non-metal, then it would replace the non-metal. Question? Because I had to. When I drop and swap, copper is a 2+, silver is a 1+. So over here, I didn't need it, right? Because it's 1 and 1. But over here, with copper being a 2+, I had to put them in. Okay. Another good question here. How did I know this was the copper with the 2+ charge? Doesn't say it anywhere, does it? Okay, I can look at nitrate charge, but if I was predicting this reaction, how would I know to use this one? I could use the copper with the 1+ charge too and not have to use these brackets. How would I know it was this one as opposed to the 1+? No, I could make it so I had enough copper. Well, but it's not, right? The silver is a 1+. Okay, the answer is, look on your periodic table. Whatever charge is listed first is the most common one. So if you're not told and there's no way to figure it out, you go with the most common one. Okay? Usually you can figure it out. But in this case, there would have been no way, and I would just go with the most common, right? The most common charge is like 98%, and the other one is very small. All right. Okay, is this reaction balanced? Okay, I got 1 copper on this side. I've got 1 copper over here. Okay, I've got 2 silvers. Okay, I've got 2 nitrates. because there's 2 silver nitrates, and I've got 2 nitrates on this side. So yeah, it is balanced. Okay, it's all worked out.
How differently would it react if the copper was
I honestly couldn't tell you because copper 1+ is so rare. Yeah. I mean, I would assume it would work about the same, but the reaction speed or rate might be greater or smaller. Okay. Last one, double replacement reactions. So in a double replacement reaction, everything is an ionic compound. Okay, both reactants are an ionic compound, both products are an ionic compound. Okay, and all that basically happens here is the metals switch places. Okay, the metals just switch places in this reaction.
Are you able to take electrons separately and add them onto different atoms?
No.
Like, would you, no, you wouldn't be able to take a copper +2 and remove an electron.
No, they're too small. They're too small. I can't just pick pieces of atoms off, right?
I was thinking maybe you should like put a certain amount of electricity through it, one make that atom or something.
No, there's no way to do that. Okay, so someone just asked, I just said the metals switch places, and somebody said, isn't that what happens in a single replacement reaction? In the last single replacement reaction, it is what happened. But here's the thing. I could have a single replacement reaction that looks like this instead. I could have, let's say, this one. Okay, I still have an ionic compound, but now I have a non-metal as my element instead of a metal. So who's it going to replace? The non-metal. So now on this side, I'm going to have Na2O plus chlorine. Okay, chlorine ends up by itself. Now, here's another thing that goes on here. Okay, with the chlorine, is chlorine special? It comes as a, well, it is a gas, but is it one of the diatomic ones? Yeah, it is, right? It comes as a 2. All right, so I've got to remember that. Now I want to balance the whole reaction. What should I start with? Yeah, probably not oxygen. Most of the time we try to avoid starting with oxygen, okay? And in this case, I think that'll probably work out. All right, so I'll start with chlorine instead. It's the next biggest number. There's 2 of them over here. How many on this side? 1. Okay, so I'm going to put a 2 here. Now my chlorine is balanced. Okay, does that make my sodiums balanced? It does, but it didn't do anything for my oxygen, did it? No. This is the problem with oxygen. It doesn't seem to matter when you do oxygen. It always screws stuff up. Okay, so we're going to back up. We're going to take away this, because this happens. Lots of times when you're balancing, you put in a coefficient and then, oh, no, that's not going to work. All right, so what I'm going to do instead is I'm going to start with the oxygens. I know that I said you don't normally do that, but I just found out that I couldn't do it the other way. So there's 2 oxygens here. I'm going to put a 2 here. Now my oxygens are balanced. How many sodium do I have? Okay, so I go back over here and I put a 4 there. How many chlorine do I have? What needs to go here? 2. All right, now everything's balanced. Okay, so you do this kind of back and forth thing while you're balancing. Okay. Yes, if chlorine is an element, that's how it appears. 100%. Yeah. All right, so that was the answer to the question. Is it always the metal switching places? Not always. Okay. In this case, there was only one metal. It had no one to switch places with, so the non-metals switch places instead. In the drop and swap, oxygen's a -2, sodium's a +1, right? So when I make that compound, I have to redrop. Sorry, I did that in my head. I didn't demonstrate it. Yeah. Okay, David? Yes, if sulfur was by itself, it would be S8, P4, right? Yeah, all of them. That's how they appear. If they're produced as an element, and this is the kind of reaction that would usually cause that, then they appear that way that we said on the periodic table. No, we don't have any. Okay, so we got here, okay, in this double replacement reaction, we have 2 ionic compounds. And we've said that in this reaction, we need to create 2 new ionic compounds. That's what's going to happen. So essentially, all we do is switch the metals, right? So now, calcium ends up with carbonate, and sodium ends up with chlorine on the other side. Okay, so double replacement reactions are actually fairly easy to predict. You just swap the metals and you've got your two new compounds on the other side.
So in a single replacement, it can be a non-metal swap.
With a non-metal, yes.
So, but this can only be metals?
Well, in this, I mean, I could swap the non-metals if I wanted to as well. It doesn't, as long as I swap the same things, I'm going to get two new compounds on the other side. I just always say, as a general rule, swap the metals. Yeah. No, I didn't say put the metals together. I said swap them. Okay, so I'm doing this. I'm taking the calcium and putting it here. I'm taking the sodium and putting it here, right? So they can't end up together. That's, again, the way I guarantee I don't end up with two non-metals and two metals together. Again, it doesn't really matter if you switch both metals or switch both non-metals. You'll get the same result. I just say in general, switch the metals. Right. Okay. Questions on how that one works? Right, so how do you predict the state? Calcium carbonate, if I go on my solubility chart, it's not soluble. So I know then that it's going to produce a solid. This is soluble, so I write aqueous beside it. Ionic compounds only react with each other if at least one of them is in solution. No, you guys won't have to worry about that. It's something that I just put on there.
On the product side, because that's also another reaction.
No, remember, it's trying to achieve the most stable state. So once a reaction has occurred, it essentially stops. Yeah, it won't typically go back. Okay. And it's not really saying that this is another reaction. It's saying I have this and this. It's not saying that I'm reacting them. This is what was produced from the reaction.
How will you know that it's with like a CaCO2 and CO2, like when they switch? How do they know that turn from like aqueous solution to solid?
Again, I just said that. You look on your solubility chart. If I look on my solubility chart, this is not soluble, so it would be a precipitate, a solid, and this would be soluble. Again, you guys aren't going to have to write them. Okay, you guys won't have to write the states of matter in your reactions, not till Chem 20. Okay? It's not like it's that hard. It's just another thing to think about, so we wait for Chem 20 for it. Okay, any other ones there, guys? Those are good questions. All right, now, when we communicate a chemical reaction, it is crucial that it is balanced. That is, that we have not created any matter or destroyed any matter. And we walked through a couple of balancing items there a minute ago. Okay, this is another balanced chemical reaction. Okay, but it's quite complex because things really move around. Okay, so for example, here on this side here, I've got 3 nitrogen dioxide molecules. Okay, so how many nitrogen atoms do I have? 3. Okay. If I go over to this side, nitrogen is in 2 different places. I still have to have how many? 3 in total. I got 2 here and, okay, so nitrogen is balanced. Okay, and I have how many oxygens on this side? 7. 6 here, plus 1 is 7. All right, 2 times 3 is 6, plus 1 is 7. All right, so oxygen is balanced as well. Okay, and then I've got 2 hydrogens on this side and 2 hydrogens on that side.
Why? Because there's only 2 things. So why would you not just put it in one thing?
Because that's not the way it goes together. Yeah, when the reaction happens, this stuff and this stuff are the products, not this. Yeah, that's going to make no sense on the podcast when someone listens to that because it was all visual. Yeah, if I gave you a reaction and asked you to predict it, all I would give you is this part. Okay, but I would give you one that's, that fits the mold pretty standard. That's not a standard reaction. Okay. All right, so the big thing here, guys, is that we have to make sure, okay, a balanced chemical reaction is one in which the total number of each kind of atom or ion, okay, is equal on both sides. Okay, so the reactants have to equal the products. No. Unless I ask you write the reaction in words, which I will sometimes. It's basically, if I'm doing that, it's basically just asking you to practice your naming. Okay, so write it in words, and I'll do that sometimes. But no, you don't have to come up with a final statement or anything like that. Okay, so these big numbers here, guys, we already said that those are what we call coefficients. Okay, the big numbers that we add in are coefficients.
If there were three compounds we're mixing together or adding together, would you do two of them first and then that compound? Or would you do them all at the same time?
You would do them all at the same time. You won't have to do that. Yeah. You might get a reaction where there's 3 products, but you won't have a reaction where there's 3 reactants. And I would never ask you to predict a reaction where 3 products were produced because that's beyond our kind of basic types. I might ask you to balance one. I would give you the whole reaction and say balance this whole reaction, and it could have more, but you won't predict because that goes beyond our standard 5 types. Okay. So here's what I want you guys to try. Okay. Let's just try the first one for now. Okay. I want you to tell me so write it down on paper and tell me what reaction type it is. Okay, is it combustion, synthesis, decomp, double or single replacement? Okay, I want you to write it out in words and balance it. Okay, this would be what you'd be expected to do, is kind of at the end be able to do that. Okay, so I'm gonna give you a minute or two on that one, and then we'll go over it together. Okay, so when we're writing this out in words, you don't put your balancing coefficients in the reaction. So let's just look first at the balancing, or sorry, at the reaction type. What kind of reaction is this? It's a synthesis reaction. All right. Now for balancing, I've got 2 nitrogens over here. I've only got 1 over here. But if I balance my hydrogens first, I think it might mess things up. Okay, so I'm going to balance my nitrogens by putting a 2 here. Okay, now my nitrogens work. How many hydrogens do I have now? 6. So what should I put here? 3. Okay, probably would have worked out if I'd have done the hydrogen first as well. But okay, all right. So we got 1, 3, 2 is our balancing. So when I write this out in words, it looks like this. It's just essentially a naming exercise. Nitrogen plus hydrogen, okay, equals nitrogen trihydride. I don't use a prefix because they're not compounds, they're elements. That's the way those elements are. They're diatomic, right? Doesn't change what they are. They're still just hydrogen and nitrogen. There are 2 molecules, but I don't have to write that. Yeah. Okay. We just want, essentially, we're just naming everything. When we write a reaction out in words, we just name it all. We don't have to tell a story. Okay. We don't have to say, 1 molecule of nitrogen reacts with 3 molecules of hydrogen, and that produces this. It takes too long. I'm not interested. Okay. I just want to know if you can name it or not. Okay. All right. You know what? That was our example. We're not going to do that one again. Okay. Try this one. Okay. What kind of reaction is that one? Yeah, it's a combustion reaction. Okay, so this one's combustion. Okay, and if we're going to balance it, what were the special rules for balancing? Balance alphabetical, and then what I usually refer to as the rule of 2. If there's an even number, I start with a 2. I don't have an even number here, so I don't have to worry about the rule of 2. Okay, so I've got 1 carbon. Now there's 1 carbon over here. So we're good there. Okay, I've got 4 hydrogens. What do I need to put in front of water? 2. A 2. All right. So that gives me 2 oxygens plus 2 more oxygens is 4. 2 there, and I'm balanced. Okay, if I'm writing this out, okay, this would be carbon tetrahydride plus oxygen gives us water. And guys, never try and name water. Okay, never try and name it anything other than water. Okay, it's just water. It's the only thing you can use the common name for, water. Okay, because otherwise it's like dihydrogen oxide, or is it hydrogen oxide, or is it hydrogen hydroxide? It's a mess. It's water. Okay, just water plus carbon dioxide. What's the common name for carbon tetrahydride? Yep, methane. That's fart gas. Okay. It's water. That's why I said it could be any of them. Just call it water. All right. Try those two. Actually, sorry, don't try this one because we already did this one. That was our example for decomp reaction. So try this one here. This is a single replacement reaction, right? All right. What's the balancing gonna be? So I've got 2 chlorines over here, and so I put a 2 there. Okay, that gives me 2 sodiums. So I come back over here and put 2 sodiums on this side, which makes my iodine work. That's always a good sign. Okay, now the whole thing is balanced. Written out in words, we'll have chlorine plus sodium iodide gives us iodine plus sodium chloride. Okay. All right, try those last 2. Okay, let's look at the next one here. So what kind of reaction type do we have for? It's a double replacement reaction, right? Okay, we got to balance it here. I would say probably best to start with either chlorine or sodium, either one. They're the highest numbers. Okay, I'm going to start with sodium. By putting a 2 there, I balance them both and the whole reaction. I only needed one number. All right, so we did that. This stuff here is calcium chloride. Okay, so calcium chloride. Pardon me? Well, there's 2 chlorines here, there's 2 sodiums here. Now I've made sure there's 2 on that side.
Why would you say the number didn't speak to both?
Honestly, I go with the one that's present in the largest number as a general rule. Usually it works. Yeah, so calcium chloride plus sodium carbonate. It gives us calcium carbonate and sodium chloride, just to save timer because the bell is going to go. All right, what about our last one? What kind of reaction is that?
Double.
It's a double replacement as well. Okay, it's an acid-base reaction. That's why we get water and a salt at the end. Okay, so this is going to be, is it already balanced?
Yeah.
Yeah, everything's a 1. Guys, if you don't see any small numbers, then there's nothing to balance. Everything's a 1, right? So it works out. So this stuff is hydrogen chloride plus potassium hydroxide gives water and potassium chloride. Okay. If you need to practice naming, work on your lab report.